Okay, so guys, let's get started. So this week we'll be going over sequence modeling. So yeah, so till now we have covered basic text processing and basic language modeling like n-gram models, and how to last lecture, like in the last workshop we went over how to convert words into vectors. So we learned dense word embedding models. So in this workshop, we'll be going over RNN celestiums and attention mechanism and basically the sequence modeling. So let's get started. So before we go on to like the sequence models, um, we'll just have a quick recap of language models, which we had already covered in one of the workshops. So what are language models? So models that assign a probability to each possible next word. Okay, so like what does ChatGPT, which you might have used, what does that do? It predicts the next token, like the next word, and assigns some probability. And from the like the vocabulary of all the words, it chooses the most probable word, right? So that is what language models do. Either they assign probability to each possible next word, or uh, they assign a probability to an entire sentence. So that is what this equation tells. Like if you have sequence of words W1, W2 till Wn, it will calculate the probability of this sequence of words, which is a sentence. So let's say a sentence key, this is NLP class, will have a higher probability than a not well-formed sentence like NLP class is this. So it will have a lower probability. Um, so and generally, there are two type of models. Not only language models. Generally, there are two type of models: discriminative models and generative models. So, what does a discriminative model do is it calculates the probability based on certain given data. So, for example, uh, you must have solved like see or seen or heard of classification problems, sentiment analysis, or sequence labeling. So it comes under discriminative model. Why? Because you are given a sentence that is X and you are predicting a Y. So, for example, let's say spam classification example. If a given email is a spam or not, so the email content will be your X. You are predicting Y based on that the content of the email, whether it is a spam or it's not a spam. Then what are generative models? So generative models calculates the probability of the input data itself. So this is not a standard notation, but generally either probability of X or probability a joint probability of X and Y. So the example like of this is whatever generative models are there right now, like Chat GPT or but all those comes under generative models because you don't have a y there, you just calculate the probability of x. And yeah, so this is also we went in one of the previous workshops. What are autoregressive language models? So all the models, GPT models that you see are autoregressive. So what does autoregressive mean is you are trying to calculate the probability of the next word based on all the previous words. For example, uh, there is a lecture going on. So if you want to predict the next word, there is a lecture going and dash. So you will predict the next word based on all the given previous words. So that is what autoregressive means. And uh, then like there is a problem like how do you calculate the next token because the context size can be infinite, right? Like it can, in theory, it can be infinite. So how do you predict that? So 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 the idea of this like slide is just to give an idea of what autoregressive means. So it just means predicting the next word based on the all the previously seen words. Um, and all the models right now, GPT or BERT, are autoregressive models, or even like multimodal LLMs. They all come under autoregressive models. So like in the previous workshops, we went over a few of the traditional language models. Not traditional, but they are not much in use now. For example, we started with count-based language models where we predict the next token based on the co-occurrence of words. For example, uh, uh, let's say you have a corpus of data where you have different sentences, and there are so one of the sentences is um, the sun is shining brightly, and a second sentence is uh, the sun rises in the east. So uh, now you here, if you want to make a model, a language model based on counting, you will see focus on the co-occurrence of words. For example, the sun occurs two times in the whole data set. So based on that, you will like model the probability of each word based on the count of that word divided by the total number of words in that data set, and like that. So whatever the most probable word is, next word is, you will write that word. So as you can see, this is not a good model because there are many problems with it. One is in its intuition itself, it thinks that all the words are independent, which is not the case, right? Like the sentences that we speak are in proper sequence. There's a relation to each word. Uh, so second thing is, since it is count based, it doesn't capture many things in linguistic. Like for example, a single word can have multiple meanings in different context. So if we are using this count based model, it will not capture that. For example, like we used this example in the previous workshops too, that the word bright can be used in different context. For example, a bright student, or bright in terms of the light, the it's too bright here. So if it comes in the same sentence, like the same data set, it doesn't capture that meaning of that word. Then we moved on to n-gram models, which are just the extension of the this count-based model, where it it counts the word based on the previously seen words. And here, as you can see, in autoregressive models, you saw that the counting starts of the previous word starts from x1 till xi minus 1. Here, it goes from like it just takes the last n words. So why is this so? Because it follow n-gram models follow something known as Markov assumption, which tells that the future is based on just the recent past history. So so on based on that Markov assumption, there are different n-gram models. For example, 1-gram model, unigram model, which is the few like it is not based on anything. It's just probability of xi. Then 2-gram models. That means the next word is based on just its predecessor. For example, the sun. So the next token sun is just based on it's not based on any other like more number of words. So that was the idea of n-gram models. Again, there are problems with these models that it will not capture, it is again based on count, right? You can see the formula there. It is again based on count. It will not capture, the examples that I just said, key, the different meanings of the same word in a data set. Or another problem with all these models are, if a new word comes in at a test time, it will not be able to handle that because it has never seen that word. So it has never come in a sentence. So it will assign the probability of zero for that new word that it has not seen before. And that's why, which is not ideal. And similarly, there are something known as log linear models. So these all are very traditional language models. So n-gram language models are still used, not as language models, but in different context these days. So n-gram models are still used, and that's why it's important to go over them, and that's why we had covered it in one of the previous workshops. So as we see, one of the main problems in all these language models are, it is not treating words or as a sequence. So that is one of the problems. We'll see more problems. So so as I said, bought and purchased, it is not putting it, it doesn't know that these capture the same meaning, these words have the same meaning. So in count based language models, we can't capture this. So one solution that people have used to mitigate that problem is they put the words in a class. For example, words that have similar meanings, or convey same meaning in a certain context, they put it in a class so that they know ki at a point they can use any word from that class and that will convey the same meaning. So that is one of the solutions that people have had come up with in the past. Second problem in all those models were, as you can see, they were probability of xi given xi minus 1. So there was, if we wanted to predict this word, we always had to consider the just the previous word. Even if we had longer context, this word always came in the context. But what if we wanted to ignore this word and just wanted to predict the next word based on, two, three, like a word from here, and we wanted to skip this word. So there was no way to do this in the n-gram models or, log linear models. So people use something known as skip drum language models, where you could skip some of the words and directly predict the next word. Then again, as I said, since it doesn't, all those language models that we saw doesn't take into account the sequence of words, it cannot handle long distance dependencies. So what I mean by that is, let's suppose you have a long paragraph and there's a reference to a person or something in the first line of the paragraph and in the last line. So it will not be able to, like think there is a dependency between the person and the reference to that person. So what people did, like these are some of the solutions that people tried, that to cache or trigger, use triggers or cache, or whatever the same words in a for a particular topic, they stored it in a same under a same class. But so as you are saying, we have solutions for all the problems. Then you might ask why we are not, why like didn't we use the same models with these solutions? The thing is that if we use all the solutions at the time, it becomes very complex and hard to decode. So that is why it was not a very ideal way to like go ahead. So people came up with different architectures. So uh, so we'll go over one of those famous architectures today, which is RNNs. So which comes under sequence modeling. So what is so like all the NLP data is sequential. Most of the data in real world is sequential. Like the characters of a word are sequential. You can't, arrange them in any other order. The semantic or syntactic meaning of the word will change. Similarly, the words in the sentence, right? You like there is a proper structure to any sentence that we see. And similarly, and so on, like sentences in a paragraph or discourse and so on. And as I said, so this is one of the examples of long distance dependencies. So he does not have very much confidence in himself. So himself and he are dependent. It refers to the same sentence. And like American English or English in general doesn't have too many so this is example of gender agreement. Like if he is used, the gender is male, the term at the end should be himself, not it can't be herself or any other thing. Similarly, if the person is being referred to as like she, then the word at the last can't be itself or himself, it has to be herself. So there are different kind of agreements that has to be there to form a proper sentence. So in other languages, let's say apart from English, in French and German or Italian, these kind of agreements and dependencies are too much. So we have to take those things into account. Another thing is selectional preference. So what does that mean is, if you read those two sentences together, these words, the rain has lasted as long as life of the queen, and the rain has lasted as long as the life of the clouds. The semantic of these both words are very similar. So how do you know which word to use in which sentence? So it depends on the context of it. For example, if the sentence, see this sentence, the context of this much is same. Only the last words the second words in those sentences are different, right? So, so, so the language model has to have that semantic understanding of which word to use based on the context. So these things like were not able to the traditional methods were not able to solve these things. So and there are other methods, right? Like other difficulties, right? Like there are the NLP natural language is full of ambiguity. For example, in this sentence, the trophy would not fit in the brown suitcase because it was too big. So what is it here? So it is referring to trophy. In the second example, it is referring to suitcase. So the language model uh, needs to have this understanding of semantic understanding of each word here. So and there are different types of predictions. So for example, you must have seen binary classification. So that is one kind of prediction. Multi-class predictions or structured prediction. So structured prediction means you have a sentence and the part of speech tagging, you are predicting the part of speech for each word. So that comes under structured prediction. In sequential predictions, there are two major kinds of there are two major types. One is unconditioned and second is conditioned prediction or conditional prediction. So it's based on probability. If it is unconditional, there is nothing in the evidence. If it is conditioned, then you are predicting the probability of an output variable y given something. So we'll see examples like what. So in unconditioned prediction, uh, uh, you have this left to right autoregressive prediction. So for example, all the transformers or even GPT, not GPT, yeah, even GPT comes under this. So why? So what is this graph representing, right? So for example, the first word is predicted based on nothing. Then the second word is predicted based on the first word, and so on. So the last word or the nth word is predicted based on the last n minus like the all the previous context. So that is one example of unconditional prediction because you are predicting x based on nothing. No y is given. So GPT does that, right? Like Chat GPT, you give the question, so it considers the whole context of whatever you have written and then answers it. So that comes under left to right regressive prediction. And as you say, transformer. So transformer is the backbone of any GPT model right now, and we'll be covering that in the next workshop. And then another example is, the left Markovian chain, which the n-gram which I talked about. Instead of the whole context, you only consider a certain amount of context, like n words, previous n words. And then there is independent prediction, so unigram model. So basically n-gram model where n is equals to 1. So you are not considering any of the previous words. You are just calculating the probability of xi. Then bidirectional predictions. So um, here you are predicting the word based on the previous words as well as the words in the future. So as you see here, probability of x is not equals to this because one of the famous examples of this is masked language models. So like there are autoregressive language models, there are something also known as masked language models and energy language models. So masked language models are, so as I said, language model is how do you like define a language model by probability of x. Any generative model is defined by probability of x. But masked language model isn't a true generative model because for a generative model, you need to define p of x and probability of x is always defined based, you always calculate probability of xi given its past, not the future. So that is why it is not a true language model as such, but people like use this notation generally to represent it. So these are like types of sequential prediction, unconditioned prediction, where you are not given a y, you are just generating x. And now this is condition prediction, where you are given y and be certain source, and then you are predicting a target y. For example, sequence to sequence model. So you can think of machine translation. You are given a source sentence and then a destination sentence, and you are trying to predict the target based on that source. So this is what this is, and this is then again non-auto-regressive condition prediction, which is basically one of the examples you can think of is sequence labeling, like the part of speech tagging, where you are given the sentence and you are predicting the part of speech for each word. So here we'll go over three major types of sequence models, and all these are autoregressive, like the unconditioned sequential prediction problems. So like there are more type of sequential models, but these three are the major categories. So first is recurrence. So what does it represent is like you have a input embedding, dense embedding, and you have a let's say a CNN or any model here, and it gives a certain output. Then this output or this here it is known as hidden state. This is used for the prediction of the next token along with the input. And why it is known as recurrent is this architecture, the parameters of this architecture are same everywhere. Like the same model is used here, 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 everywhere. That's why it's known as recurrent neural networks or recurrence. Then, yeah, convolution. So convolution, you might have heard CNN. It's very, very famous in image classification or speech problems. But in sequential modeling, recurrence and attention are the dominant models right now. Convolution, not so much. It is used generally, as I said, in image and speech processing. The reason being, in language, every token that you have has a semantic meaning as such. But if you take an image or a speech, like tokens, so what is image? A collection of pixels, right? So a pixel will not have that much semantic meaning. So there, like running a convolution network is much more, intuitive, because then you like run a convolution and then the pixels or the feature maps starts making sense. In language modeling, generally recurrence and attention models give good outputs. So here, that's why we'll go over recurrence and attention mechanism in this workshop. So let's start with recurrent neural networks. So as I said, recurrent neural network means you have a context, or let's say you have a word and you are trying to predict the next word. So let's so you take the input embeddings of a certain word, let's say of each word, like my name is dash. So you will take the input embedding of my, the name and is, and then you will have a certain network which will predict a hidden state, and then it will be that hidden state information will be passed on to the next word embedding, input embedding, and then similarly till you reach the last stage. And when you reach the last stage, then you will predict the label, what will be the like the next token, next word in the sequence. So this is how you use RNNs as a language model. Yeah, so we'll see like the architecture in detail for RNNs. So let's say you have so RNNs can be used in multiple ways. The architecture is very flexible. So here, as you can see, at every time step, you have a certain output. So you can think of it as a, it can be a part of speech problem where you are trying to, predict the part of speech for certain all the words, or you can also think of it as a machine translation problem of a fixed length, English to Spanish or some other language, where each word is being converted to its respective counterpart. So Y is the translated version of X, something like that. Or if you just want to predict the next token, or you want to use RNNs as a language model, you don't predict Y1, Y2. You just at the end predict the last token here. So and what each, so let's So as I said, each this architecture for each sequence is same. So let's just consider this part, and let's see what the actual architecture of RNN is. So xt is the input at that time step t, and ht minus 1 is a hidden state till t minus 1 time step, and it contains all the information till that time step. So as I was saying, giving the example of next token prediction, my name is dash. So if you want to predict the last token yt, the last word, ht minus 1 will contain all the information till my name is. So for example, if you x3 is the token, y3 is the token you want to predict, ht minus 1 will contain all the information till this point. Then xt is the current input. You will take the embedding of that input, and you will have a certain weight matrix W, and then to like encode or augment the current input with the previous with the information you already know, you will have a certain matrix U. So you will take the multiplication of U with the like the hidden state information xt minus 1, and you will add it with the current input embedding, and then you'll apply some activation function to get the hidden state information at that time step, and then again you will multiply it with V to get the prediction at that time step. So this is it looks complicated, but it is very, very easy. Like you can see the the pseudo code for this. It's you just you are taking like you can think of it as you are taking the information till t minus 1 steps, and you are adding it with the current input, and then you are just applying the activation function and predicting the token or the label. And so, for example, if this xt was x1, whatever ht you have calculated, this will be passed on to the next word, ht minus 1. So for x2, ht minus 1 will be h1. And like this, you will calculate at each time step the prediction or the output embeddings. So yeah, so for training, as I said, so based on the task, you have different loss function. So here also like gradient descent will be used, and so this is the the task for next word prediction. So let's say you are given a first word so, and you are trying to predict the next word at a time at each time step. So you will convert this input embedding of so, and try to predict the next word. And so in RNN, there are, or in general in auto-regressive language models, there are two main concepts that people follow, and most of the research at this time is going on to how to improve these two things. One is self-supervision and teacher forcing. So what teacher forcing means is, so let's say it predicted certain word at time step 1. Okay, so it can be right, it can be wrong. So, but the thing is, at the next time step, you need to pass it as an input. If you are, if you consider this task of next word prediction, so you only have so as the first word, as the given word, which is true. You don't know whatever the prediction will, whether the prediction will be right or wrong. So if the prediction is wrong and you pass it as it is, so what you can train it in that manner also. But what people generally teacher forcing means is, whatever the output for that time step, at the next time step, you will always pass the correct, the ground truth value for that. So even if, let's say, the prediction at this time 1 would have been something instead of long, small or something else, at the second time step, you will always pass the correct ground truth value. So that is known as teacher forcing. And it is not only the property of RNN language models, it is general across all the autoregressive models. And then there is something known as self-supervision. So, so you know what supervision models like supervised training is, right? Like you are given X and Y. So whatever Y prediction that you make, you compare it with the ground truth value and then calculate the loss. But here, you don't need to have that Y ground truth value, because the next word in the sentence is the like the correct word. So you don't need to label each sentence into something with something. For example, so you are trying to, predict the each word in the sentence. My name is Rajat or something. So after my, you don't need to have ground truth value for the next word. You already know the next word as name. So that is self supervision. Like the sequence of words will be its own signal, like supervision signal. So that is known as self supervision. So this concept is used in RNN also, and in general autoregressive models. So and again, so the training happens. So you the training happens in the very like traditional way. You predict the next word and compute the loss. So based on if it's a classification problem, you will compute the cross entropy loss, or or you can calculate maximum log likelihood, or different loss functions depending on the task. And so at each time step, whatever the loss you get, you just add it, and that will be your total loss. And then you will do back propagation. So this in RNNs, the back propagation is known as back propagation through time, BPTT. It's a famous algorithm. So it's the same, nothing much. You like how you do in CNNs or any other model. You will calculate the gradient with respect to the the last prediction, and then you will write a chain rule and update the gradients for all the weights. Yeah, so as I said, if RNN you want to use as a language model, you give the next word as the input and you predict the next word. And yeah, one more thing. So this is what also, so this is autoregressive generation also, not only for RNN generation. So even in GPT or chat GPT, what happens is whatever question or let's say you are asking the chat GPT to summarize a paragraph. Okay. So instead of this input token S, you will write the whole context here, and then it will try to, predict the next word and try to summarize it. So the richer the first token is, and this is what the second point here is telling. Like the key to these approaches is to prime the generation component with an appropriate context. That is, so if you don't have anything, like no context, you just give it you just make a input token, so that this is just a symbol that this is the start. And and if you have a context, then you write it here, and then it will give better results because it will know the context. So you can understand this in a more intuitive way. For example, if I ask any of you to just speak, you will not know what to speak, right? You can speak out anything. You won't know. But if I give you, okay, tell me about yourself, or tell me about how was your day, you will have certain context and you will be able to answer it better. There's the same thing. So if you will have a context, the outputs will be better. And this is not only for RNN, this is for any autoregressive models. Now, yeah, so this is a very, very famous, and I think most of you might have heard about it. This is a very famous problem in RNN, vanishing gradient and also exploding gradients. So what happens is, as I said, if you try to mathematically write the equations for back propagation, what will happen is you will try to find the gradient of the loss with respect to the output. Then again, then with respect to H3, then with respect to H2, H1, and H0. So what you will do is basically if you write it mathematically, there will be at the end a term will come which will be of the form lambda and W. If W is the weight matrix, W to the power T. So when you multiply certain like weight matrix which have lower values, let's say if you are multiplying 0.01 with 0.002, so the result will be even smaller, right? So, so let's suppose you have a long sequence of 20 or 30 such sequences of RNNs, and you multiply such smaller values continuously. So at the end, what will happen is still here, the gradient will become zero. So if you keep on multiplying 0.02 into 0.001 continuously, at the end, the result will be very, very small, and that will not be enough to update the weights. So how do you update the weights is, if let's say X or A is the weight, you update it by the original value minus or plus alpha, which is the learning parameter, into the gradient. So if the gradient is very, very close to zero, there will be no update in the weights. So, and if there are no update in the weights, that means the model is not learning. So we don't want that. We want the model to learn at each iteration or each epoch of the training loop. So, so, so that is known as vanishing gradient. There is the opposite of this, exploding gradients, where you multiply two like matrices which have huge numbers. So the result will be huge. So in that case, also the result will. So as I said, the a term comes in backpropagation lambda w power t. So if the result is too huge, so for the modern computers, it's not like it will not be able to store that huge value. So it will just store a garbage value or list out a garbage value. So so like even for exploding gradients, what you can do is there's a solution. You can just clip it or normalize it. But vanishing gradient is a bigger problem because you don't know what to do. You can't normalize it because it's already very, very small. So that's why RNN works well for small context. But if you have a very huge context, it won't like work very well. So that's why so a better version of RNN is something known as long short term memory, LSTM. So it solves that problem by uh, by the idea of something known as called as gates. So what gate, the idea of gates it is it controls the flow of information. So in RNNs, like you had the information. So for example, here the information from the first time step zero was traveling like this. So the information from here was passed on to the H1, then the H like the time step three, like that. So there in LSTM, after every like at every time step you will have gates, multiple gates, input gates, output gates, write gates. So for example, there's a forget. So you calculated at zero. Let's suppose you calculated at zero. So now you want to pass the information to H1. So let's try to think of it as a in a very intuitive way. There's a very famous example that people give to explain LSTMs. So for example, this is a whiteboard, and I write all like fill the whiteboard with different things, and then I ask you to like go through it and understand it. So it will be very, very hard for you to understand everything if I've written it in random orders here in the whiteboard. But what if someone already like tells you ki, okay, in this whole whiteboard, this part of information is important, then this part of information is important, and this part of information is important. Then you can focus on those respective parts and then forget about all the other parts on the whiteboard. So same here. So we want something, the gates, to tell what part of information that is contained in S0 is important. So you do selective forgetting. So what that means is whatever information is there in H0, what is not important, you forget it. So that's why there is a gate, forget gate. Then there is a gate, input gate. So what it means is whatever information is there, how much of it you want to pass it on to the next hidden state. So that is input gate. Then output gate is what part of the previous time step you want to update the new time step with. So so that is what all these things are. This is F is forget gate. So in the original LSTM, there were only three gates: forget, input, and output. But a new version of RNN or LSTM came where four gates were used, where G is the update gate, and this became the like the widespread, very, very famous LSTM version. And many people now call this as the LSTM instead of the original one, but the original one only contained F, I, and O. So here, as I said, you take HT minus one, and you have a gate F. You apply sigma. So and you so F. Think of gates as a vector. So you will initialize it with random values, and and during training, even the gates will be updated to learn the correct components. So let's say at the end, forget gate value is 0.5. let's say there's only one value in the vector, 0.5. What it means is you are only considering half of the previous information that was there in st minus 1. So, and this is what like all the gates have different functionalities, and so here I would not go much into the equations. The equations are very different. What you are doing in, let's say, forget gate is you define a vector u and you multiply it with st minus 1, and then you add it with the current time step information, and then you update the u such that it will and you use a set point function as the activation function, and then you update u in each at each training time, and that becomes your forget gate. So like, so you just need to understand what because there are many versions of RNN. This is one of the famous versions, but like this, there are many versions of RNN and also LSTMs. So you just need to understand it in an intuitive way. What is the information? Like, what is the purpose of these gates? So these gates are just meant for flow, like to regulate the flow of information. Okay. So now okay, I'll first go over GRU. So GRU is again the same concept. So the difference between LSTM and GRU is GRU is again a version of RNN. So here you don't have the forget gate. You only have output and input gates, and you then multiply the output gates. So here, let's suppose this is instead of H here, it's S, the hidden state at t minus 1 time. You're multiplying it with the output gate, and you get, so that is basically what information from the previous time step you want to pass on. And then you have current, like the current time step xt value, and you then multiply it and pass it through a sigmoid function, and you get s tilde t. Then what part of this you want to pass it on to the next layer? You multiply it with it, the input gate, and then you add it here with again the previous state information. And instead of forget gate, they use 1 minus it. So that's so, and in LSTMs here there is like forget gate. So like this, you can have like multiple gates, but again the key idea is to regulate the flow of the information. Like you don't want to the burden the next time step with all the information. You only want the important information to pass it to the next state. So again, so you saw RNNs, LSTM, GRUs, and we saw that in RNNs there was a problem of vanishing gradients. So even LSTM and GRUs are RNNs at the heart, right? So why does vanishing gradient doesn't happen here? Like, can any of you tell? Like, or like, can you think why? Like, how does GRU or LSTM solve the problem of vanishing gradient? Because they are also acid. So this is one time step. Again, this will be again recurrent. Like this will again unfold into many time steps. So why do like how do LSTMs and GRUs solve that problem? So the idea, okay, no one. So the idea here. So why it flew? So think of it this way. Okay, I'll again go back to the RNN. It's easier to. Yeah. So for example, suppose here there are gates also here at every time step, and you get some loss. So as I said, what purpose do the gates solve? They regulate the flow of the information. For example, at time step 0, generally there's not much like too much information that will be passed on to the last layer. The information from H0 that will be passed to H3 in LSTMs or GRUs is very minimal. So, so when the loss is propagated backwards, since no information from H0 or very minimal information from H0 was passed to H3, so even if the like the gradient that is passed to H0 is very small, it is not a problem, right? Because only a small information was anyways passed to H3, and as I said, the gates regulate the flow of information. They also regulate the flow of gradients backwards. So if X amount of information was passed from H0 to H3, only X amount of information gradient will be passed back to H0. So that is how, like, that is why LSTM and GRU is like don't have the problem of vanishing gradients. because they have gates which regulate the flow of gradients also. Yeah. So let's see encoder decoder. RNNs can also be used as encoder decoders. So for example, till here you saw, uh, if you want to translate a sentence from English to something, this is a fixed length. If in English a sentence is of 3 words, the output also has to be of 3 words. This so what, but generally this is not the case, right? A translation can have multiple words or multiple, like it can be of variable length. So so that is why you have encoder decoder, where you encoder is like the basic idea of encoder decoder is that encoder takes the input and uh, creates a context out of all the information that is given in the input. And then all the information that the encoder has encoded is passed to the decoder, which decodes the information and gives the output. So let's see how RNN is used as encoder decoder. For example, this is again a machine translation task. So and this is a very, very famous architecture. Like till recent times before transformers came, RNN, this model was used for machine translation at like even in industries. So, for example, you had n length sentence, and you want to translate into a sentence which is of length 4 in a certain word. So you will like encode the information in these hidden states. And since you don't want to convert it at this time step, you don't need to have a like the classifier here. So at the nth time step, you will encode whatever information will be here, will be then passed to. So this like the nth hidden state will contain the information of the whole sequence of input. Now the whole this information will be passed to the decoder, and then it will start generating the output one by one. So the problem here is this layer is known as the bottleneck layer. The reason being, what if the information here is not enough? Or, if it is a long sequence, what if the information at the nth hidden state doesn't contain the information at one of the time steps which was necessary for translation? So that's why it's not known as a bottleneck layer. And to solve that, the mechanism of attention came. If you read the first attention paper, it was based on the task of machine translation, uh, and they used so RNNs have different versions. Like there are stacked RNNs, there are bidirectional RNNs. So so the basic idea of attention is, for example, if you have a given input sequence and given output sequence, at this, if you are decoding this at time step 2 in decoder, you only want to focus on certain words which are important to and output this word at time step 2 decoder. So that was the idea of attentions. So here, how it will solve the problem of bottleneck is, instead of like using this information for all like for decoding at all the time step in decoder, will only use certain time steps. Like it will give attention to each attention weights to each of the time steps in encoder for each, and whatever is important in encoder at each time step will be used for decoding. So and there are like majorly two like varieties of attention: cross attention and self attention. Self attention is the is what transformers are based on, that we'll cover in the next workshop. Today we'll just focus on cross attention. So cross attention is okay. Time is up, so we'll cover it in the next. Yeah, so you can scan this and solve the question. So you might there's a leaderboard.
Workshop. So what we do is we do a leaderboard of thoughts where all these answers will be collected, and top 3 winners will be given a prize towards the end. So make sure to. Also, another quick